Hello, welcome to this video about motion under gravity. In this video, we're going to take an example, we're going to solve it, and hope to understand and gain insight into the various ways the three equations of motions can transform and the amount of information we can evaluate using just those three equations. Alright, so let's begin. So in order to do that, let me get rid of this elaborate structure right now. Pretty little snowflake. Anyway, now that that's gone, well, there's a pod fair. Alright, so the thing is, we are given a surface like so. This represents the Earth. Well, it's blue for a reason. And you throw a ball from the ground. Now this is at ground level, so initial height of the ball is 0. And you throw it such that you throw it vertically upwards with a velocity of 30 meters per second. So 30 meters per second in the vertical direction in the arrow that I've drawn there. Now with this velocity, the ball reaches a maximum height somewhere there. Let's call that height h max. Now at this point, h max is a scalar. 30 meters per second is also a scalar, but along with the directions, they are both vectors. So the ball reaches a height of h max at some time interval, and we are expected to find the position of h max. So the question asks us to evaluate what h max is. It asks us to evaluate where the position of the ball is at time t equal to 1 second, 2 seconds, 3 seconds, and 4 seconds. And also, when will the ball reach the ground again? Because we know that once we throw a ball in the sky, it reaches a maximum height and then goes down. So we are asked to find the total time interval of the flight. So we also asked to evaluate what happens when the ball reaches back at the ground. What we can also do is we can find out what the v final velocity would be, but let's keep that on the side and work with these three questions for now. Alright, so like always, we need to set our coordinate system and we need to have our equations of motions at our fingertips. Now the equations of motions are, well, v equals u plus at, s equals ut plus half at square, and the last one is, well, v modulus square equals u modulus square plus 2a dot s. So these are our equations of motion in the vectorial representation. Now this is quite uncommon to find, however, these three equations represent every bit of information we would need to solve this problem. I work with vector equations because they are better than the one-dimensional case in which all the vector signs over these variables of v, a, and s are removed, because they work much better in this form. Now, we also need to establish our coordinate system. So our coordinate system, let's make a coordinate system in such a manner that the vertical direction is positive and the horizontal directions to our right is also positive, very much like our x and the y coordinates. So if you're measuring distances in the negative direction, that means in this direction, our vector would be negative, and if you're measuring in this direction, it would also be negative. So this is how we define a coordinate system. However, we would only be using this right there because our motion is completely vertical. So that's a bit of insight into the problem, and now let's dig in and get to the crux of the matter. Alright, so what do we know about the ball right now? Well, so our agenda in hand is to find h max, or the height at which the ball stops moving. So that's the height at which the ball's velocity is 0. So v, whatever this is 0 at this point, and v here is going to be 30 meters per second. Now, v is a very general variable I'm only using in the diagram. I'm not using in the equations. In those cases, we will have different variables to deal with. Alright, so our initial velocity would be u vector, and that would be 30 meters per second plus I cap, or I hat. Now that means our initial velocity points upwards, so that's in the plus, oh wait a second, that would be j cap. And j for a reason, because in the y direction the vector that points in this direction is represented by j, and the vector that points in this direction is represented by I. So we have 30 meters per second j hat or j cap. Alright, so for this motion, when the ball stops there, we would have the final velocity to be 0 meters per second. Now, it doesn't really matter which direction we want to point this in, but for the time being, let us just call that plus j cap. Now that's the direction in which 0 meters per second points. So now we have final velocity, initial velocity. What about the acceleration? Well, the acceleration always points downwards. So the acceleration would be a, and that would be negative g. Negative g, j cap. So that is how acceleration will be represented. Because we know that since acceleration always points in the negative direction, hence in this direction, it should be negative to the j cap vector. We could always write this as negative 10 meters per second square j cap. So this is the value of a vector that we would be using. And if you notice, I have approximated g to 10 meters per second. Now, in reality, g happens to be 9.81 meters second square inverse, but we can approximate this to 10 meter per second square like that as well. So it doesn't really matter. It makes the mathematics a bit more easy and helps us get the answer quicker. But the approximation is very close, 9.81 to 10, not really bad, not very terrible. We can work with that. So acceleration is done, velocity final is done, and velocity initial is done. What can we use using these three variables? Well, I see the first equation here, and that uses these three variables and only leaves t unknown, so we can find t using that. So let's find the total time it takes to reach the top. Now, initially, the time was 0. Here, we are asking to evaluate the time at that point where the ball suddenly becomes red for some reason. Well, I'm just kidding. That is where the ball reaches the maximum height, all right? So it's right at that point. Now, we have 0 meters per second, j cap, which is v, equals 30 meters per second, j cap again, that's u, and acceleration is negative 10 meters per second square, j cap, that's a, times the time t. Now this is the time t it reaches the top of its motion. Well, we can get rid of meters per second, and the time is measured in seconds as well, so you get meters per second here as well, and you cancel that out throughout. The j vectors get cancelled out as well. So basically you're left with a scalar equation of 0 equals 30 plus negative 10 times t. You can solve this up, and you know that whatever t is going to be measured in seconds. So at this point, when the ball is at 0 seconds, it's on the ground. At this point, the ball is going to be at some value of t seconds when it reaches the top position. So solving this, we get, well, 30 equals 10t divided by 10, you get 3 equals t, or t equals 3. Now this means that at 3 seconds, remember, because we're measuring the time in seconds, the ball reaches the top. So therefore, at t equal to 1 second or 2 seconds, the ball would be somewhere there. And at t equal to 3 seconds, the ball would be there. At t equal to 4 seconds, the ball would fall back down somewhere there. So these are what these time represents. 2, 1, 2, and 4 would be when the ball hasn't really completely exhausted its vertical velocity. At 3 seconds, it would have exhausted its vertical velocity, and that's why v equals 0 at that position. And at that point, the ball would be at the top. Now, we know that the ball will be at the top in 3 seconds. 3 seconds is what it takes to go all the way. It takes for it to displace h max from the base. But can we evaluate what that height would be? Well, we could do, now that we know a, v, u, and t as well. So let's note that down somewhere, that the time it takes is 3. Well, they've already done that. Let me get rid of this for the moment then. So with that away, we can focus on to evaluate what would be the s vector. S vector is the displacement vector, and that should give us information about h max. Alright, so let's have that. So our displacement vector from 0 to 3 seconds would be something, and that should indicate h max. And that should be equal to ut plus half at squared. All we need to do is just input the values. So that would be 30 meters per second in the j direction, that's u, and you have t, well, that would be 3 seconds plus half, and a will be negative 10 meters per second square, j cap, and t square. That would be 3 times 3 seconds square right there. So what we have in this equation is a vector equation right now. So we get s vector equals, well, cancel the seconds, cancels the second there. What we can also do is we could do a bit of mathematics there. We could have 3 times 30 would be 90 meters, j cap, plus this by this makes 5, 5 times 3 times 3, this is 9, 9 times 5 is 45, so that gives you negative 45 meters j cap. So this is essentially taking two vectors, one 90 meters and the other one 45 meters in the opposite direction, in the j cap direction. So that gives you s equal to 90 minus 45, and that's nothing but 45 meters in the j direction. So this tells us that in 3 seconds the body would have traversed 45 meters in the j direction. That is to say that this vector from the bottom all the way to the top would be a vector of magnitude 45 meters and would point in the positive direction right there, parallel to the j vector, because you have plus j vector right there. So now we know at t equal to 3 seconds, h max would be 45 meters, and that's all the time it takes for the ball to go all the way to the top. So now we have a couple of information. Now we know how long will it take for the ball to go to the top. Now, but they also ask us to evaluate the capital T, which is the total time it takes for the ball to fall down. If you think about it, the time it takes for the ball to go up would be the same it takes for it to come down. And if you don't agree with me, we can always solve that to clarify that. But I would just want you to develop this intuition that if you send a ball with certain velocity up, it will stop and then it will fall down after reaching its maximum height. Now, those two motions are completely identical, and therefore they take the same amount of time to travel. So if it takes 3 seconds to travel up, it should take 3 seconds to travel down, and I would therefore approximate or would somehow indicate that the total time should be somewhere around 6 seconds, because that is 2 times 3. So let's just keep that in our heads. However, we should also prove it professionally and using the equation that we know, because they give us better answers most of the times. Alright, so at this point we are almost done, halfway at least, with our problem. What's left to do is to find what happens to the ball at 1 second, 2 seconds, and 4 seconds. So let's do that. Alright, so let me change the color of the pen to green. Alright, so we're asking ourselves, where is the ball present at 1 second, 2 seconds, 3 and 4? We have already answered at 3 seconds the ball is at the top, and all we had to do was use this equation right there. Now if you look at this equation, it gives us the position vector of the ball, and all it takes is the input of the initial velocity and the acceleration. And if you substitute different values of time, which is given in our question, we will get different answers. So that tells us the s is in fact a function of time, which it should be, and that is equal to ut plus half at squared, and that's all that we need to evaluate the position vectors of the ball at all of these time intervals of 1, 2, 3, and 4. So let's evaluate s at 1 second. That would be same thing as before, 30 meters per second. The time would be 1 second, and you're measuring that in the j cap direction, right there, plus half, a would be negative 10 meters per second square, and time would be 1 times 1 second square. So that would be t square, so that's still 1, because 1 square is 1. What you get eventually is the fact that s of 1 second would be, well, seconds goes by seconds, second square goes by second square. You're left with 30 meters in the j cap direction, plus, well, 10 goes by 2 gives you 5. That is to say, 2 times 5 is 10, and negative sign right there gives you negative 5 meters, again in the j cap direction. And I forgot the j because I was being careless. This is j because this is the vector of acceleration. So this is j right there. That is why the j gets carried on. You get 30 minus 5 eventually. So that's 30 minus 5 meters in the j direction. That gives you, well, 25 meters in the j cap direction. So we know that initially we calculated that the ball would rise all the way to 45 meters in the sky and then start falling down. And at time less than that, it would be on its way to the 45 meters height. So if it's at t equal to 1 second, the ball would be somewhere there. It would be 25 meters in the sky going in the vertical. So at this point, we can also hint that the velocity would be positive in the sense that it would also be pointing upwards, because at later time, the ball continues to rise, and it's only at this height that it starts to reduce, that it has already exhausted its velocity and then starts to fall down. So this is what s of 1 second would look like. This is the displacement vector, from the original position to the final position at 1 second. That is your vector of 25 meters in magnitude in the positive z direction. So that is how you would go about it. We can do this similarly for 2 and 4. Let's do that quickly. S of 2 seconds, again, would be, well, 30 meters per second, because that's the same initial velocity. J cap, always, times, well, 2 seconds plus half of acceleration, which would be negative 10 meters per second square, and j cap right there, and t square would be 4 seconds square, because 2 times 2 is 4. What we can do at this point is to cancel out the seconds as before, second squared as before, and we get 30 times 2, 60 meters in the j direction, plus 4 by 2 is 2, and 2 times 10 is negative 20. Negative 20 meters in the j direction. So again, you're getting a positive vector of 60 and a negative vector of 20. You're left with 40 meters in the j cap direction. So this position, the ball would be, at time 2 seconds, the ball would be from the base all the way to this position, somewhere there. That height would be 40 meters, right there. So you see it's very close to the final position, and in the next second, the ball would travel 5 meters to go all the way to the top. So that is how you would get s of 2 seconds. Eventually, we have to find what s of 3 seconds would be. Well, s of 3 seconds, something that we've already calculated before, would be, well, we know that that's 45. So that's 45 meters in the j direction. But what about s of 4 seconds? Well, s of 4 seconds happens to be initial velocity, which is 30 meters per second plus j cap direction times the time, which is 4 seconds, plus half of a, which is negative 10 meters per second square, again j cap direction, and times t squared, and that will be 16 seconds square. Alright, same thing as before, cancel in seconds by second, second square by second square, start evaluating. 30 times 4 is 120 meters in the j cap direction. 2 and 16 gives you 8, so that's 8 times 10, that's 80, with a negative sign, meters in the j cap direction. So there you have it, that is the total. Now, if you evaluate this, this is 120 minus 80, that is 40 meters again. So wait a second, this tells us that the ball is back at this height, the same height as this vector. Well, that actually makes sense, because since the ball was at 40 meters at 2 seconds, at 4 seconds, the ball went all the way from top and started to fall down there again. So now, the vector that represents its total displacement would again be the same as what we had for at 2 seconds. So that would be the same vector of 40 meters pointing vertically upwards. So therefore, s of 4 seconds vector is exactly identical to s of 2 seconds. They are both 40 meters, and they both point in the positive j direction. So that is how you would make sense of that. Alright, now quickly, let us try to confirm that at 6 seconds, the ball is back at 0. So let's try to do that. Alright, now when the ball is back at 0, which is here, let's say it takes time capital T to go there. So finally, S of capital T is what we're trying to measure. Now, since the ball went all the way to the top and then back to the bottom, what do you think the displacement vector would be? Well, the displacement vector would be final minus initial, and since they both are at the same height, displacement vector should be 0. So that should be 0 meters in whatever direction you want to measure. Let's say that's j cap. So this would be S of t when the ball has finally hit the ground after having looped its motion around the 45 meters of maximum height. Alright, let's try to see if that's the case. So we want to solve for t when s is 0. This is what we're trying to do. Again, we put in the values that we know. U is 30 meters per second. T is capital T, seconds. And they both point in the j. Oh, sorry, only U points in the j. The product of both of them still points in the j. Plus half of negative 10 meters per second square, right there. And that also points in the j direction, so nothing strange with that. And you have t square, second square to go with that, right there. Alright, what do we do with this? Well, do the same thing that we've been doing for the 5 times before. Seconds goes by seconds, second square goes by second square, and you are left with a vector equation. Now you see you have j vector on both the sides, cancel that out, like so. You have meters on all the sides, you can also cancel those out, like so, and you're left with a scalar equation of 0 equals 30t plus 2 for 10 and 2, that gives you 5, and a negative sign gives you negative 5. T square still holds as c square. So this is your equation, and in order to solve this for t, what you can do is you can take t common out, and that gives you 30 minus 5t. You can simplify this by dividing the entire, and this is equal to 0. You can simplify this by dividing everything by 5, so like that, and you're left with 0 by 5 is 0, t like so, and this whole equation by 5 is 6 minus t, and that is 0. So what you have right now is a quadratic equation, and a quadratic equation has two roots. One of them is 0, the other one is t equal to 6 seconds. So the total time at which the ball goes back to its original position is at 6 seconds, but this equation also gives us another value of 0 seconds. And what does that mean? Well, that means that at 0 second 2, that is exactly when the motion started, the ball would have also traversed 0 meters, which is trivially the case as well. So that is to say that that at 6 seconds or at 0 seconds, the ball is back at its initial position. And if you want to consider the total time interval, well, it should always be the greater value of the both, and that would be 6 seconds in this case. So our intuition that it takes the same amount of time to go all the way to the top and the same amount of time all the way to the bottom are the same. Therefore, the total time would therefore just be the sum of both those durations, which was 3 plus 3, and that was 6. And we have also confirmed that by using the second equation of motion to confirm that. So there you have it. That is how you would do a question like that. And that is how you would go around dealing with motion under gravity. So I hope this video made sense. I hope it helped you understand how we can manipulate these different equations. And just these 3 equations can give us so much more amount of information than it seems. So all the best and have fun.